working on her bachelor's in science in agriculture, where she graduated with honors from the University of Peradeniya. Peradeniya. Did I say that right? Yes. So originally Sri Lanka. All right, so Peradeniya is in Sri Lanka. She has a Master's of Science in Food and Agricultural Sciences from the University of Maryland Eastern Shore, and a Doctorate of Philosophy of Food Science and Technology from the same university. She comes to us with a tremendous amount of experience as a lecturer from the University of Maryland Eastern Shore, but also from the Warwick Community College out that way, and presently from Salisbury University, where she teaches introductory biology. She teaches anatomy and physiology lecture and lab, as well as microbiology lecture and lab. And of course, as usual, I like to get some inside scoop on our speakers. Dr. Munasinghe is super into her family, and she loves eating and preparing meals with them and for them. So she's, from what I estimate, a very caring mother and wife. So that keeps her busy when she's not actually attending to student needs. And she tells me that if she's not in the lecture room or lab, she's actually in her office doing office hours, constantly meeting and speaking with students. So I thank you for being with us today. And the title of her talk is A Comparison of Different Collagen Extraction Methods and Analysis of Chicken Collagen to Form Collagen Films. Welcome, Dr. Munasinghe.
Thank you very much, Dr. Sosa. My name is Kumudine. Title of my presentation today is a comparison of different collagen extraction methods and analysis of chicken collagen to form collagen films. Collagen is a naturally occurring fibrous protein, commonly found in both humans and animals. It is the most abundant protein in animals, and approximately 30% of animal protein consists of collagen. Collagen is called universal glue that holds your body's connective tissues together. In addition, it provides structural support for bones, skins, tendons, ligaments, and blood vessels. However, as you age or as a result of injury or trauma, your body's collagen begins to be weakened. The results can be as simple as wrinkles on your face or complex as loss of control over your body's excretory functions. Collagen has a wide range of applications, including leather and film industries, pharmaceuticals, cosmetics, biomedical materials, and the food industry. Further, there are many commercial products on the market today that contain collagen. These products are represented by hand and body lotions, nail treatments, firming gels, wrinkle injections, eye pads, and also anti-cancer treatments. Why do we care about collagen? The global market size is projected to reach $6 billion by 2025, according to Grandview Research. There are 20 different types of collagen. Each one has specific structural and functional properties. For example, we can extract type 1 collagen from skins. Type 1 collagen has two identical alpha helix 1 chains and a alpha helix 2 chain with slightly different chemical composition. The most common motif of collagen has a glycine, proline, and hydroxyproline sequence. Collagen has to solubilize first and then reconstitute to form collagen films to protect its initial original properties. Among all the benefits come off of collagen films, collagen dressings play a key role of each phase of wound healing. It attracts fibroblasts and keratinoblast and enhance angiogenesis and reepithelialization. Moreover, Wallace et al. In 1993 found that collagen films can inhibit bacteria. It indicates a special interaction may involve between binding sites of collagen molecules and microorganisms as well. At the present, bovine and porcine are considered as main sources of collagen. But the outbreaks of all these mammalian sicknesses, such as bovine spongiform encephalopathy and foot and mouth diseases, have given bad impact among the users of collagen and collagen-derived products. Therefore, increased attention has been paid to non-mammalian alternate sources of collagen. My first research question was, can chicken collagen be used as non-mammalian collagen? In Eastern Shore, we have a lot of broiler chicken farms. So I thought of extracting collagen from chicken waste, undervalued chicken byproducts, such as skins and bones. My next question was, which extraction method gonna give me the highest collagen yield? So I used 5 different extraction methods, all traditional methods and 2 new methods to extract chicken collagen. And my last question was, what type of biophysical properties gonna get from chicken collagen films? Raw material preparation and pre-treatments were adapted from Kittipatana Bhavan et al. In 2004. I cut chicken skins and bones into smaller pieces, as you see it in the picture, and then I measured initial protein content, fat content, and inorganic material contents. And then I used 0.1 in sodium hydroxide to remove non-collagenous protein for 6 hours. And deproteinated samples were defatted using 10% butanol for 24 hours. And then I remove inorganic materials using 0.1 in hydrochloric acid for 24 hours. After the pre-treatment steps, I again checked protein content, fat, and inorganic material contents to see the effectivity of my pre-treatment procedures. Here's my traditional methods. I extracted chicken collagen with acetic acid, citric acid, and sodium hydroxide. So to accomplish that, I used pre-treated samples, of course it is skins and bone samples, mixed with each individual solvent, and then used double layer cheesecloths to filter the sample, and filter rates were collected and subjected to further precipitation procedure. Now collagen is dissolved in the solvent now. And I used 2 new techniques. I used pepsin to extract collagen. Pepsin, we can extract pepsin from, it's a stomach enzyme. What pepsin does is that pepsin breaks protein into polypeptides. So I use 2 methods. One is called one-step acid, one-step pepsin extraction, and the other one is 2-step acid, 1-step pepsin extraction procedure. So for one-step acid, 1-step pepsin extraction procedure, pre-treated samples were mixed with acetic acid containing pepsin, and then filter rate was used for further precipitation. For the 2-step acid, 1-step pepsin extraction procedure, I mixed the sample with acetic acid first, and then I collected the acid solubilized collagen first, and then residue was re-extracted with acetic acid containing pepsin, and finally both filter rates were combined and used for further precipitation procedures. I use sodium chloride to precipitate collagen. I mix sodium chloride in my filtrates. Particularly it was 2.6 m sodium chloride helped me to precipitate collagen. So then I use centrifugation, the method, to collect the precipitate. And now in this precipitate we have excessive, like lot of salt. I use dialysing technique to remove excess salt. I used 10 volumes of acetic acid and distilled water to remove salt through the dialysis technique. And then finally I freeze dry the sample to remove water and use freeze dried samples for further analysis. Now on the top I have a picture for my filtrates. And here we have collagen, chicken collagen extractions. So chicken collagen, as you see it in here, very white and no objectionable smell in chicken collagen. So I didn't have to worry about disguising the smell using fragrance or something else. Now that I have a collagen extracted from 5 different extraction procedures, I use SDS page to analyze proteins in each extract. So what I did was, actually SDS page is an electrophoresis method that helps us to separate proteins based on their molecular weights. You must be familiar with that. Now what I did was, I mixed freeze-dried to 0.2 milligram of freeze-dried sample in sodium phosphate containing urea and the SDS, and then 5 microliter of treated samples were loaded into the gel, and then electrophoresis patterns were visualized using cyclorubis stain. I checked hydroxyproline content as well. Now, hydroxyproline is a non-essential amino acid. Hydroxyproline forms from hydroxylation of proline. Here I had the hydroxyproline molecule. So, without this OH group, hydroxyl group, that's proline. Why hydroxyproline is important for this research? Hydroxyproline stabilizes alpha chains in the collagen molecule. And also, the others use hydroxyproline content as a conversion factor to find out collagen yields. So I directly extracted collagen, and I didn't think about that part, but I wanted to see hydroxyproline content because hydroxyproline stabilizes these alpha chains. I checked chicken collagen solubility in different pH levels and also different sodium chloride concentrations. You know, I use acid, and then I use sodium chloride after having these results. Now, to see the effects of pH on collagen solubility, I mix my samples with either sodium hydroxide or hydrochloric acid to set pH, get a pH range from 2 to 10. And then I centrifuge the sample and got a supernatant that has soluble collagen, and use supernatant to determine protein content using Bradford assay. To determine the effects of sodium chloride levels, I mix equal volume of collagen and sodium chloride with different concentrations, and then again supernatant was used to determine the soluble collagen in that. Now I analyze collagen. Now the time is for me to make collagen films. So freeze-dried samples were mixed with acid and carboxymethyl cellulose to give the strength to these collagen molecules, and then I mix the slurry with glycerol, that's a plasticizing agent, and glutaraldehyde, that's a cross-linking agent to give more strength for collagen molecules. And then after that, I poured the chicken collagen slurry into plastic trays, and after overnight drying, took out these films and used conditioning steps. I dip these films in a hydrochloric sodium chloride and distilled water, and after that I air dried filters until the water activity reaches to 0.08. And after making collagen films, I use TAXT2 texture analyzer to analyze these filters. These two tables just show us protein contents in skin and bone samples. I used 0.1 in hydrochloric acid to remove non-collagenous proteins after doing several preliminary studies. So this is the most effective concentration, 0.1 in sodium hydroxide to remove non-collagenous proteins. post-skin protein content was 62.7 dry weight basis, and post-bone protein content was 30.4% dry weight basis. I used 10% butanol to remove fat content from my samples. With butanol, fat always make clumps and floated the top solution. So it was easy for me to remove fat from the samples periodically. So post-skin fat content was 1.5, post-bone fat content was 1.4 after the pre-treatment. Inorganic material content in skin was very low, but I checked final fat contents for both skin and bones. I had 0.7% of fat in the sample. Collagen yields for all different extraction methods. I use acetic acid extraction, citric acid, sodium hydroxide, one-step acid, one-step pepsine, and two-step acid, two-step pepsine extraction procedures. Now, as you see in the board, pepsine extractions gave significantly higher collagen yields. These are dry weights. More than 38% of collagen could be extracted from pepsine dilutions. But when I compare these two extraction methods, two-step acid and two-step pepsine extraction didn't give me the significant difference than the one-step acid, one-step pepsine. But two-step acid, one-step pepsine extraction method take longer time, 24 hours long. So I used collagen extracted from one-step acid, one-step pepsine to make collagen films. These are the results for bone collagen yields. Again, we see the highest yields with pepsine digestions, but comparative to skins, bones didn't give me much of the collagen, but still I want to analyze bone collagens as well because I'm extracting collagen from chicken waste. So I really want to continue this research analyzing bones. SDA space results.
Question. I'm trying to, can you place it in context for me? Like the numbers that you were showing us, are they comparable to, say, earlier you showed like bovine and porcine sort of being used to make some of these films?
Yes.
Is that comparable? Are those numbers that you come up with comparable to what was found in samples of, I'm assuming,
very close, not the equal, but very close.
it depends on the quantity of starting material, right?
Definitely, definitely. But I used 120 grams in each sample. But if I increase the quantity, definitely the percentage also going to be increased.
And so then it seems like you're moving towards the making the collagen films. Ultimately, you took us through the methods of it.
Definitely.
The concentrations that we've seen so far, is that concentrations that you want to see in collagen films that may be used as Band-Aids, if you will? In other words, it's a concentration of collagen films that you're making for purposes of therapy.
Definitely.
And if so, are the concentrations of collagen in those films what we would use on a patient?
Yes, definitely. We can change the concentrations, but if we can, my target was to find out, to extract enough collagen to make collagen films or collagen injections. So get the most out of it. That was the target.
How much is injected at a time?
Actually, I'm still didn't have a chance to work on that part. I'm sort of staying in the initial stages, trying to extract as much as the collagen as much as possible, and then later on I'm gonna find out all those details. All right. So STS page analysis. I had molecular weight markers. Well, molecular weight markers have known molecular weight, protein with known molecular weights. And I compared molecular weight marker with my collagen. Second lane has calf type 1 collagen. I purchased that to see how calf collagen looks like and what's in there. And lane 3, 4 and 5 is acetic acid, citric acid and sodium hydroxide extracted. Lane 6, again I have acetic acid. But when I compare these bands with calf type 1, they are more or less similar. I see 2 identical alpha 1 chains and then alpha 2 chains, and still I had to work a lot, but see a lot of similarities. And on top of that, traditional methods give higher molecular weights. The molecular weights that I have here is more than 100 kilodaltons with traditional methods. Now the 7th lane and the 8th lane have 1-step acid and 2-step acid extractions. So they didn't have bigger molecular weights. They have less than 66 kilodaltons when you compare the shorter molecular weights with bigger molecular weights. But these results are in agreement with Nalinion et al. In 2007. He also saw the fact that pepsine digestions give smaller molecular weights than traditional extractions for chicken skins. Hydroxyproline content. I had all 5 extraction methods, and hydroxyproline content in chicken stays between 5.8 to 5.9 milligrams per gram. So it's been noticed that I noticed the fact that calf and bovine collagen has 13 to 14 milligrams of gram hydroxyproline content. And I started reading about this and found out 1994, Bishop et al. Showed that collagen content is increasing with the age. So I use broiler chicken collagen because of the shorter, narrower lifespan. I believe chicken collagen doesn't have a lot of bigger count for hydroxyproline content, and now I had to think about how I'm going to improve the stability of the film without hydroxyproline content. But again, I can use more sensitive methods to determine hydroxyproline as well. Collagen solubility with different pH levels. Highest solubility was obtained at pH 2. It was 0.16. Chicken collagen acted as the same as a typical protein. Now, typical proteins, when pH is low, get positive charges. When pH is high, get negative charges. And same charges repel each other, and solubility is higher in all these two ends. But in between, pH levels make the proteins to have a net neutral, like zero neutral charge, like, how should I say that? Net charge in this part is zero, no charge. With lower pH levels, we get positive charges, higher pH levels, we get negative charges on protein, and in between, we don't have charges on protein molecules. They have a trend to make clumps and get settled. That's why I have higher solubility at pH 2. Here comes the solubility with different sodium chloride concentrations, where collagen solubility decrease with increase in sodium chloride. So there are several reasons for that. Sodium chloride can compete with protein for water. And also, sodium chloride can neutralize protein as well. Then protein get aggregated and get settled. But when I make decisions about precipitation, like quantities for sodium chloride that I use for precipitation and use for conditioning steps, I considered this. I considered 2% and made decisions for precipitates. These are the readings that I have for my collagen films. As a start, I check two things. One is hardness, the other one is brittleness. So bigger number for hardness is good, and hardness is the peak of the graph. And brittleness was checked as a distance to maximum force, distance from zero to the peak. So if the distance is longer, that tells us that it is less brittle. So this is hand homogenized, non-filtered condition film. So the figures are really good. Maximum force is 3,262 J, and distance to maximum force was 30.5 millimeters. Let's look at the other filter that I have. This is a very thin film. It is hand homogenized, non-filtered condition thin film. It is very hard. At the same time, it's very brittle. Look at this one. Hand homogenized filtered non-condition film. So maximum force was 500 G. It is not hard. It is not hard because it didn't go through conditioning steps. Yes, hydroxyproline content is lower, but we can improve the structure of the collagen film by sending these films through conditioning steps. So I know for sure right now, after working with this part, with these films, condition steps are very important for these films. This is hand homogenized, filtered and conditioned film. Look at these figures. This is very good. It's a conditioned film. Having a bigger number, maximum force was 4,102, and distance to maximum force is 26.7. It's a very good filter. And here comes my newest film. It's machine homogenized film. It still have to improve a lot because maximum force is very low, distance to maximum force is very low. So I'm reading and finding ways to improve this film nowadays. In conclusion, I would say chicken collagen can be used as a non-mammalian collagen, and molecular weights were higher, more than 100 kilodaltons for traditional extraction methods with acetic acid, citric acid and sodium hydroxide, and molecular weights were lower, smaller than for pepsin extractions, that was less than 66 kilodalton. Highest solubilities were obtained for 2% sodium chloride and pH 2. Hydroxyproline content is 5.8 to 5.9, and solubilities were obtained for pH 2 and 2% sodium chloride was the highest, and maximum mechanical properties could be obtained for conditioned film. So still have to analyze bone collagen, and then I need to find out full profile of amino acids, and still have to make bone collagen films, and then I'm going to compare, as Dr. Sosa told me, like I had to compare chicken collagen with the bovine and porcine collagen films and all the other characters, and towards the end, target is to find a route to carry chicken collagen to make wound dressings and injections. I use these references, and so far I have 3 publications related to this study. I really like to thank USDA Evan Allen's project for supporting this research, and my sincere gratitude go to Dr. Carter Dennis, Dr. Mark Holland, Jeffrey Ruto, and Matthew Whitaker, who's always helping me with this research. And I'd like to answer any of your questions related to this.
Why did you pick collagen to study? Because that seems like a very specific, and I don't know how you would connect, okay, collagen, let's go.
Yeah, it was in a way accidental. I like reading, I always read. I saw how much other people having interest towards collagen. They try to talk to any person in Asia, in Europe, in Like everywhere, people have that interest. Let's make collagen. Collagen is natural, and we are so worried about how we look, right? Senescence is the struggle nowadays. So people are really curious about collagen. Then I thought, I am close to SU. In the Eastern Shore, we have a lot of chicken farms. I thought, okay, let's find out whether we can extract collagen from chicken. If this is successful already, but if this work, if I carry chicken collagen to the end as much as possible, then it is going to bring low-cost chicken collagen. So you can remove these worry lines by having bovine injections. One injection is $800. Or you can extract your own collagen. Physicians can do that, own collagen and make an injection. It's $1,500 worth. And donor collagen from a dead person is $1,200. So I'm trying to extract collagen from chicken waste materials. So in a way, I can diverge collagen with the waste materials, plus producers going to have a increasing revenue. A lot of benefits. That's why that made me to start this research, and apparently students also really enjoy the fact that they can see things when they work with me working on this research.
I had two quick questions.
Sure.
Why are you using chicken collagen specifically of all the other non-mammalian options? Why chicken?
Yeah, that's a very interesting question, like hers. Now, people from Asia started extracting fish collagen. And when I read the publications, I realized that fish collagen has very low denaturation temperature. So one of my targets for next 5 years is find out this thermal stability of chicken collagen. So I still have to work on that, but I know for sure, since chicken just stay terrestrially on land animal, chicken must have to have somewhat low body temperature than ours, maybe 38 degrees or 37 degrees. So if that made me to think about chicken collagen. Because a lot of people just non-mammalian, as soon as somebody says non-mammalian, they just extract collagen from fish. That is what happened. Even though collagen is everywhere in every animal, in skins and bones. Did I answer your question?
Yeah. The other question was, you mentioned that your primary goal is extracting like as much collagen as you can.
Yes.
But when Dr. Sosa asked earlier about the concentration in the Band-Aid films, or if you're using injections, if you don't know what the concentrations or the desired concentrations for those are, how do you know how much would be an ideal amount for you to extract?
You mean concentrations of injections?
That, and then just in general when you're extracting collagen, what's your target goal?
How to manipulate concentrations in the injection? Or?
Right, and what's an ideal amount for you to extract?
There's no, I don't know. I can't say this figure is ideal. At this point, I just try to extract as much as possible, extract collagen as much as possible, and then go from there to see the connection between concentrations and the collagen in the injection, I believe.
So I guess how are you studying that exactly?
Huh?
How are you looking at the link between that?
Injections and
and what you collect?
That's a very good question. I think my ambition gonna be after collecting collagen, I'm going to see what's going to happen, what is happening in the injections, and based on that, I'm going to like manipulate my concentration into theirs, I guess. But still, I have to do a lot because I don't have no publications to like sort of find out support. No, because of that, I really, you know. So when you ask that question, I'm gonna like, okay, this is another route I need to, right? But at least at this point, I know we can extract chicken collagen. But that is a very good question. I'm going to work on that.
So you're mentioning fish, and I know that they use fish collagen to like treat burns and things like that. Is that something that could possibly be done with chicken collagen?
If it is possible, I love to hear that. But still this research staying in the initial stages, and still we had to improve the collagen films and all of that. Still it's very new. So maybe down the road I can get those samples like injections and all that and analyze what's in there and find out the concentrations of collagen they use to make injections. It is not like just collagen, you had to add different things like I used carboxymethyl cellulose to make these molecules interact with each other properly. So likewise, when they make injections, they had to add several other things now. So I believe later on, I'm going to sort of compare contrast products with the concentrations and with my collagen films. So.
I'm sure other students have questions, and I have like
Yes.
4, but we have to move on.
Yes.
Thank you.